let a rational function, f of x, be written as g of x over h of x. We know that the limit of f of x as x approaches h is equal to the limit of g of x over h of x as x approaches h. Consider an instance where x approaches 0, and g of x and h of x gives 0 by direct substitution. Then g of 0 over h of 0 is indeterminate. This is the same in the case of infinity over infinity. This gives rise to the Bernoulli rule, also known as L'Hopital rule. In limit, the L'Hopital rule allows the derivative of the numerator and the denominator of a function, given that the function yields an indeterminate form by direct substitution. The L'Hopital rule is applicable if and only if the function gives an indeterminate form. On this condition, we can conclude that the limit of the function, g of x over h of x, as x approaches a point for which the function is indeterminate, is equal to the limit of the function g complement of x over h complement of x. Let's take this basic example for better clarification. The limit of x squared minus 4 over x minus 2, as x approaches 2. By directly substituting the value that x is approaching, we have the following. 2 squared minus 4, over 2 minus 2, this gives 0 over 0. Because of this indeterminate result, we are good to flow with the question using the L'Hopital rule. What we just need to do is to differentiate the numerator, and also differentiate the denominator, then take the limit. The question gives 2x minus 0, over 1. We can now easily apply our limit from here, and we arrive at the result, which is 4. This is how the L'Hopital rule works. It is very important that one knows how to differentiate well before considering this method of taking limits. The L'Hopital rule is a variant of differentiation. If the numerator and the denominator of the function is a complicated expression, will you be able to stand the derivative? Differentiation is the foundation. You need to revise it. Let us consider another example. The limit of sine x over x, as x approaches 0. This is a well-known function, whose result has been taken as an identity. There are many ways of arriving at the answer, but in this case, we want to solely prove the result by L'Hopital rule. Start by substituting the limiting value, which is 0. Sine 0 over 0 is equal to 0 over 0. An indeterminate form. This guarantees the usage of the L'Hopital rule. So, we need to derivate the numerator, sine x, and the denominator, x. And this gives the limit of cos x over 1, as x approaches 0. This gives cos 0, and the answer becomes 1. Therefore, the limit of sine x over x as x approaches 0 is 1. Let us consider another example. The limit of 1 minus x raised to the power of 1 over x, as x approaches 0. By substituting the limiting value, we see that the function gives 1 raised to the power of 1 over 0, which is another form of an indeterminate expression. But let us be reminded that the L'Hopital rule only applies when we have our indeterminate expression in the form of 0 over 0, or infinity over infinity. To be able to use the L'Hopital rule, we need to make this function appear in a form that will give either 0 over 0, or infinity over infinity. Since u is equal to e raised to the power of ln u, the trick is to write our function in the way. So, 1 minus x raised to the power of 1 over x is same as e raised to the power of ln 1 minus x raised to the power of 1 over x. By concentrating on the power, we see that 1 over x will come to the back of ln 1 minus x, from the law of logarithm. This can be modified to give e raised to the power of ln 1 minus x over x. So, the function given in the question can be written in this format. Let us go back to the question and substitute the function with the result we have here. We have the following: lim 1 minus x raised to the power of 1 over x equals the limit of e raised to the power of ln 1 minus x over x. By focusing on the power, we see that it gives ln 1 over 0, which is equal to 0 over 0, when the limiting value is substituted in it. This means that we can apply the L'Hopital rule to the power. Let us consider the power separately. The limit of ln 1 minus x over x as x approaches 0, gives the derivative of the numerator and the denominator. This is equal to ln 1 over x minus 1, over 1, which is now a reduced function that can be evaluated by direct substitution. It gives minus 1. The limit we just evaluated is the power. The power is minus 1. Therefore, we draw the conclusion that the limit of 1 minus x raised to the power of 1 over x is equal to e raised to the power of minus 1, or 1 over e. You do not need to cram the steps, you just need to understand the reason behind each steps. Let us consider another example. Example number 4. Evaluate limit of sin x raised to the power of sec x as x approaches pi over 2. We see that sin pi over 2 gives 1, and sec pi over 2 gives 1 over 0. Therefore, sin pi over 2 raised to the power of sec pi over 2 gives 1 raised to the power of 1 over 0. This is just like the previous case we considered. We are going to apply exactly same idea here. We will write the function in term of the exponential number and the natural logarithm. We have e raised to the power of ln sin x raised to the power of sec x, which is equal to e raised to the power of sec x ln sin x. Recall that sec x is equal to 1 over cos x. So, our expression becomes e raised to the power of ln sin x over cos x. This is just the simplification of the function. Now, let us return to the question, and evaluate the limit using the result we already have. The question becomes lim e raised to the power of ln sin x over cos x as x approaches pi over 2. Now, the power of e meets the criteria for L'Hopital rule application because it gives ln sin pi over 2 over cos pi over 2, which gives 0 over 0. Let us bring this power down and treat it separately. The limit of ln sin x over cos x as x approaches pi over 2 is equal to the following by differentiating the numerator and the denominator separately. This is just like any other question we have solved. It is important you know to apply the L'Hopital rule. It is very useful for evaluating cumbersome series. This simplifies down to minus lim cos x over sin square x, as x approaches pi over 2. By substituting our limiting value, it gives minus cos pi over 2, over sin square pi over 2. This still further simplifies down to minus 0 over 1 square, which is equal to 0. The power which we just evaluated is equal to 0, this means that the expression is equal to e raised to the power of 0, which is equal to 1. So, our answer here is 1. There are two more examples to discuss before we close this discussion. Example number 6. We want to evaluate the limit of a raised to the power of x plus b raised to the power of x plus c raised to the power of x over 3, all raised to the power of 1 over x. By direct substitution, the function gives a raised to the power of 0, plus b raised to the power of 0, plus c raised to the power of 0, over 3, all raised to the power of 1 over 0. This gives 1 raised to the power of 1 over 0, an indeterminate form in disguise. Let us perform our method of conversion, which always expose the disguising indeterminate form. The limit becomes that of e raised to the power of ln, a raised to the power of x plus b raised to the power of x plus c raised to the power of x over 3, over x. The power now gives 0 over 0 when tested with the limiting value, so we need to apply the L'Hopital rule to the power. The limit of ln a raised to the power of x plus b raised to the power of x, plus c raised to the power of x over 3, over x, by the definition of L'Hopital rule, we have the succeeding line. No matter how long the expression is, the method of solution remains the same. The only challenge you may find therein is in the aspect of differentiating the numerator. This is where the knowledge of differentiation comes in. That's why it is important you understand the crook and crannies of differentiation before diving into the pool of limits. By differentiating the numerator and the denominator, the following expression surfaces. Lim 3 over a raised to the power of x plus b raised to the power of x, plus c raised to the power of x into bracket a raised to the power of x ln a, plus b raised to the power of x ln b, plus c raised to the power of x ln c over 3, all over 1, as x approaches 0. I would love to write this on a new page. By following due process, you will discover that this is of no difference to what we started with. The method of solution remains the same. Now, let us substitute our limiting value, which is 0. The following result protruded, by observing the fact that a raised to the power of 0 is 1, b raised to the power of 0 is 1, and c raised to the power of 0 is 1, with the assumption that a, b, and c are not equal to 0. C. They're simplified as ln a plus ln b plus ln c over 3. By the rule of logarithm, we have ln a bc over 3, which is equivalent to 1 over 3 ln a bc. By the rule governing the power, we derive a conclusion that 1 over 3 ln a bc is equal to ln cube root of a bc. Don't let us forget that the result is for the power only. Now, let us return the power. The result becomes e raised to the power of ln cube root of a bc. Natural logarithm eliminates the exponential number, and our result becomes the cube root of a bc. The steps are clear and easy to comprehend. L'Hopital rule helps in the advanced and the elementary aspect of limit. So we draw a conclusion as follows. Here is one more example before we round up this lecture. Example number 7. We want to calculate the limit of the root of 1 plus x square raised to the power of 2023, minus root of 1 minus x plus x square raised to the power of 2023, over x, as x approaches 0. By substituting the limiting value, the function gives 0 over 0, which is a reason to apply the L'Hopital rule. The method of solution does not change for this question. Like any other, we just have to differentiate the numerator and the denominator separately. This is something you can cheaply calculate somewhere. The answer can also be directly written by one who understands the nitty-gritty of differentiation. When you differentiate each of the terms, the results become lim 2023 over 2 times 2x plus 1, root 1 plus x square raised to the power of 2022, minus 2023 over 2 times 2x minus 1, root 1 minus x plus x square raised to the power of 2022, over 1. I would love to write this on a new page. I believe that the steps we took before arriving at this stage is as crystal clear to you. So, we have our expression here. The next step is to substitute the limiting value of x, which is 0. By substituting 0, we see that lot of junks leave the expression, which moderate our result to 2023 over 2 minus 2023 over 2 times minus 1. This is same as the sum of 2 halves of 2023. It is equal to 2023. So we can now conclude that the final answer to the problem is 2023, thus the conclusion above holds. Don't forget to subscribe and share this lecture with your colleagues that are finding it hard to understand the crook and crannies of L'Hopital rule.